so less energy. So people are so tired after 3 days of boring talks, is it? No? Yes? Okay, so today is the last day of the workshop, so let's make sure that it is as fun-filled as the last 3 days or the past 3 days, and also keep the questions coming on and all those things, right? So, yeah, so it's my pleasure to welcome our first speaker, Vijay. He is a professor in the Department of Computer Science and Automation, this department at IISc. He received his PhD in computer science from Duke University and holds the BE degree in computer science and MSc degree in mathematics from BITS Pilani. By the way, some of the attendees are from BITS Pilani. His research interests include scientific visualization, computational geometry, and computational topology. In current work, he is developing topological methods for time-varying and multi-field data visualization and studying applications in biology, material science, and climate science. Over to you, Vijay.
Thanks, Sumit. Are you able to hear me? Okay, good. So, like Sumit said, fourth day, so I think you realize the importance of coffee. And this coffee should get stronger over the days, I think, so you can wake up. So this is, since it's the first talk, I think I try to keep it as visual as possible. It's also true to the topic and perhaps to the time of the day. So the title, as you have already seen, right? We'll get to the title, but I want to start off by talking a little bit about what we do here in the department within the Visualization and Graphics Lab. So we are a group of computer scientists, mathematicians with varied interests, some very theoretical, some interested in system building, some interested in analyzing data, some interested in actually being useful to a domain scientist by building technology. And we come together to develop visualization tools and techniques. So what is visualization? Visualization refers to the creation of visual representations of your data towards aiding you to understand the data better, understand underlying phenomena better, and perhaps if you know already the phenomena, it helps you to communicate those understandings to others, right? So that's the role of visualization. We work on visualization in a scientific context where the data comes from various science and engineering applications. And you see a sample on the screen here. The visualizations could be data that come from imaging modalities, such as what you see on the left, from material science, to data that comes from simulations, such as what you see next, which comes from fluid dynamics, the study of flow and so on, to cosmology, the study of the large-scale structure of the universe, and in chemistry, something which we have done very recently, and towards the right, structural biology, studying molecules, proteins, and channels within these macromolecules. So the applications are varied, but what binds all of this together in our group is the kind of techniques that we apply towards generating these visualizations. So we are a group which really likes to understand the shape of space, right? So in mathematics, this is studied under the topic topology. So we use ideas from topology, which is a very old branch of mathematics. We look at it from the computer science lens. So we design algorithms for computing these topological structures. We design algorithms for not just computing these structures, but also designing efficient representations of these topological structures, designing methods for querying from these structures, from comparing these structures, from removing noise from these structures so that they are useful in practice, and of course presenting them in a visual form such that it is useful for domain scientists. I am not going to talk much about topology today. Much of that is under the hood. I am going to instead talk about the visualization system that we developed in one instance, right? So before I start into the topic, of course, I want to thank everyone who was involved, the funding agencies for sure, but the people who did much of the work. The topic that I'm going to talk about, which is ocean data analysis and visualization, has been a long-standing project which is collaboratory between our group and a oceanographer, Vinay Chandran, who is at IISc, and a HPC expert, Satish Vadyar. So this has been long-standing, together with other visualization experts, Tala and Ingrid. Much of the systems and the techniques that I talk about today are the work of Ravindra, more recently, prior to that, Toshit, and then Upkar, and Deepu. These are students, project staff, and so on, who came from our group and who are doing great things now. So let's jump in and try to understand what is this, the topic of today's talk, right? So ocean data analysis refers to analyzing data that relates to the ocean, that comes from the ocean. And when I talk about analysis, I'm going to focus on visual data analysis. Why visual? Visual representations allow the oceanographer to identify patterns in the data, and hence capture features, important characteristics in their data, and perhaps use that to drive their hypotheses about different phenomena, and then go on to test those hypotheses. It allows for, visual analysis allows for an exploratory study, right? As compared to something like a confirmatory study, where you have hypotheses and you want to go and test those hypotheses, right? So if you want to explore and find various phenomena, then visual analysis is something that you want to start with. So in that context, I present some pictures also here. So this is a picture of some distribution over the ocean. Can anyone guess what am I showing here? There are enough clues there. If I click on the next button, you get the answer, but can you venture a guess? So this is something over the ocean for sure, right? The land is kind of all dark and uninteresting here.
Petroleum.
Petroleum? Okay, that's a good guess. Why do you guess that?
And darker on the Middle East.
Say that again, please.
Middle East, it's a bit dark.
Oh, okay, it's dark, much darker. No. So the dark region are just black, which is the land, which is uninteresting for this study. But water is interesting, so which is why you see some of the river systems in the land, right? So let's look only at the ocean. The clues are in the ocean, right? Look at regions that you're familiar with. Is dark. So there is a color map on the top. Maybe you can use that to infer. Temperature, okay. So is Bay of Bengal cooler? You would think that the North Atlantic is cooler, right? So that's, say that again, please. The depth of the ocean, we all know where the Mariana Trench is, and the Pacific and Atlantic, right? It's much deeper. The Bay of Bengal is definitely not very different from that. Any other answers? Say that again, please. Pollutants. Yeah, okay. So that's yeah, okay. We are less polluted. Maybe if you want to think of it like that, right? It's low. Blue is low, by the way, right? And green and yellow are higher values. What else do you think about when it comes to ocean and the water? Why is it different? So compare it with the river water. Salinity, right? So that's the clue, right? So the river water is blue. It is fresh water, right? So this is salinity. This is a salinity map. And you see that the Bay of Bengal, this is from November, by the way. This is just from 2 days ago. This is almost real time. I can generate another picture of this for today as well. It won't look very different. But it'll look different in the summer, a little bit, right? So ocean salinity does change, right? It's not as salty in the Bay of Bengal as it is in some other parts, right? And you see that along the currents, for example, in some places, the salinity is low, right? But how is this? But overall, we know that the salinity is maintained in the ocean, right? It doesn't get altogether fresh water, right? Bay of Bengal is not really fresh water, But why do you think Bay of Bengal is less salty, at least at this time of the year? What could be reasons? Rivers flow in and give a lot of fresh water. Where else does fresh water come from? Rains, right? And when does it rain in the Bay of Bengal and in India in general? Right? In the summer, when we have the summer monsoon and the retreating monsoon, right, which gives a lot of rain over the bay, right? So we saw the cyclones coming recently, right, that hit Telangana, so and Andhra Pradesh, not Telangana. So salinity. So that's the topic of today. We are going to study salinity distribution, particularly in the Bay of Bengal, right? And how is it maintained, right? So, but what are some challenges, right? So, in terms of computation, in terms of building visualization systems, the data size is very large, typically. So, we'll talk about that. We'll make it more clear. There are complex features that one has to study, such as what are called eddies, which are big vortices, your whirlpool-like structures, but at the scale of hundreds of kilometers. Many of the features that you see in the ocean are not well defined mathematically, right? So it's very difficult to convert that into an easy algorithm or a simple algorithm to compute. Often these phenomena do not depend on one field like salinity, they depend on the interrelationship between multiple fields, right? So these are some challenges. We don't address all of them in this talk, we address a couple of them, the first and the third, for example. Right? So, in addition to all that I said, ocean data also is changing over time. The salinity changes over time, the velocity, the currents do change over time. So, it's important to visualize these temporal fields, right? And for this talk, since we introduced salinity, we are focusing on so-called scalar fields, scalar valued fields, right, that change over time. An animation such as what you see here or a video is very good, it's useful, it provides a good overview, but it's restricted to that, it provides an overview, right? So if you take a class on visualization, and especially when we talk about time varying data, it's counterintuitive, but one of the more useful visualizations of time varying data are not videos, but they are static images, which tell you what happened during the entire duration, right? We are not good at recall as much as we are good with mnemonics. What you see here is again salinity, but the color indicates depth here, right? So somebody mentioned depth. So this is something about depth, but it tells you the depth of high salinity water, right, in the Bay of Bengal during the summer. So you can see that close to Sri Lanka, the depth of the high salinity water is more, right? It's kind of diving in and then surfacing up a little bit as it comes closer to the coast, right, towards Visakhapatnam. So these are all the pockets of high salinity water, right? And this is something that Vinay Chandran has studied extensively over 20-30 years and has figured out how the salinity in the Bay of Bengal gets back to the average, even though we have a lot of fresh water coming in, right? So this is one of the phenomena that they have studied painstakingly, right, with various measurements and so on. We would like to understand this a little bit better and perhaps find some new, make some new observations. So the challenges with time varying data are that the physical features are difficult to define, like I said earlier, but in addition, they are evolving over time, right? So this, for example, what you see on the right is what I would like to capture and track, right? This is a very complex feature, very difficult to define clearly, right? And then you want to track them, right? And of course, the large data sizes make it also difficult computationally. So here is the problem statement. We would like to develop a visualization framework or a system and methods for tracking features and for visual analysis of the movement of HSC, which is high salinity core, which is a technical term used to represent the high salinity water that we said, and in the Bay of Bengal, right? So, so those are the two acronyms that I use. So the HSC or the high salinity core does evolve in shape and in size. That makes it difficult. And we also want to be able to handle large data sizes, right? So this is what I'm going to talk about. I'm going to present solutions primarily with respect to methods for this, to address this problem. And later I will talk about a framework which works slightly in general towards exploring ocean data. So let's jump in. We talked about the problem. Let's talk about the data, right? Where does this data come from? These are all available thanks to many decades of work. There are standard formats where the data is available. NetCDF, some of you may have heard of this. Not a very surprising name, net for network. Common data format, something which is common. So we use 3 data sets at different resolutions. The way you study, you read this is the 1/12 of a degree refers to the latitude and the longitude resolution. So you have data along a grid, and so at the resolution, which means that the separation between 2 lattice points is 1/12 of a degree. So this is 1 degree is approximately 111 kilometers, right? So you can work this out. 200 meters is the depth to which you make the measurement. So these are not measurements; these are simulations. There are some measurements included, but we will not get into that. 122 is the number of time steps. So in this case, days, but you could have data at 6 hourly and much more finer resolution, right? So that's how you read this. And as you see, that as we go down, we have higher resolution data. The ROMS is the state-of-the-art product available out there, which gives very high resolution, close to 1 kilometer, and that's what we use. This is also something that the HPC collaborators have supported, right? So this is not easy to generate such data. So that's another problem altogether. What you see on the top right is actually from GLORIS, the temperature map. Somebody, I think you mentioned temperatures. That's how temperature looks like, right? So in case you are interested. So by the way, all of this is available at the click of a button. You can just go to Copernicus and Ocean Marine Review, right? So and there are tools available to just look at the data as it's available, right, for today, right? So this is near real-time data. What are the solutions? We developed a method for tracking the salinity by introducing a notion called a front and then designing algorithms for tracking this front. The oceanographer doesn't want to stop there. They want to understand what causes the salinity to move. Is it currents or is it just diffusion? So we had to redo everything to understand the role of currents in this salinity movement. So an advection-based approach for tracking. So all of this led to a general system for visual analysis of salinity, which is also an integral part of the tracking algorithm. Like I said, data sizes are a big challenge. So to address this, we have parallel and distributed algorithms. Right, so I'm going to talk about a couple of them here, primarily the front-based tracking and the visual analysis, right? So that you get a sense of at least 1 or 2 methods in detail. So here's version 1.0, which is just your overview, right? So here is the high salinity core. This is the same picture, same video that you saw in the earlier slide with a little bit more detail. The color map shows the depth. And this you see the date also. This is in 2016, but this is kind of true in most summers. So July through September. The video is running fast. We have data on a daily cadence. But what you see is that, again, the same phenomena. There is salinity at greater depth next to Sri Lanka, and then it moves north, right? We would like to move forward from this. This is just still an overview. We would like to do something better, right? And in order to do that, we track fronts. So here is the overview of the method. and I'm going to give you a description of the algorithm in a visual form, so that we can finish quickly and have time for questions. So we extract an iso volume, which is a collection, a sub volume, which consists of high salinity. So this is called an iso volume, and we use a threshold 35. 35 refers to the average salinity of the ocean, right? Hence 35. Then we create a coarse representation of the high salinity core from this volume, and as a next step, we want to extract the boundary of this region, right? Which is like a surface, and from within that we would like to extract that part of the surface which has some kind of a predisposition to move north, right? So that's the very high level intuitive idea behind the algorithm. Okay, so with that we will be able to understand how the high salinity water is moving. So the first step, we extract the high salinity water, then we extract some kind of a bounding surface, and then we segment that to identify the part that is moving northwards. So pictorially, so here is an iso volume. These are top views, right? So these are all algorithms that work in 3D, but I just show you the top views. So an iso volume, for example, would look like this in like early July. So you see it's much over the Indian Ocean, not even entering the Bay of Bengal here, right? So the boundary of this looks like the red region here, right? So these are curves in 2D, surfaces in 3D. We segment this boundary to identify the north-facing regions, right? So this is a segmentation algorithm that uses a variation of a near neighbor classification. Once you identify the north-facing boundary, this is what we call a front. We stitch together these fronts across different depths to get a surface front, right? Again, all of this is based on a combination of near neighbors together with some careful representations that allow for efficient construction, right? So that's not something that I'm going to be talking about. So this surface front is our basic entity that we would like to track. So this surface front is available at each time instance, and multiple components of them are available over the Bay of Bengal, right? By the way, we restrict our attention to Bay of Bengal. The algorithm does work in other regions, but since the focus here is on the phenomenon from Bay of Bengal, we apply it to that particular part of the ocean. So the surface front evolves over time, and this is represented in the form of a graph, a track graph, which is a directed acyclic graph, right? So the track graph, which is what you see on the right, the visualization of the track graph is not really useful, but it just gives you a sense of how complicated or how complex this can be. So the track graph's nodes represent the front at every time instance, and edges in the track graph represent evolution of or potential evolution of one surface front across time, right? Now from within this graph, we would like to extract the individual, like the evolution of individual pockets of high salinity water. This can be extracted as long paths, so specifically single source, longest paths within this graph, right? So that's essentially what we do. We extract those tracks, and we get the tracks from the Bay of Bengal, and those tracks look like this. I'm just showing some of the tracks here, right? So some of the long tracks, and since the tracks are available over 3D,
How do you get the nodes of the graph?
right? So the nodes of the graph are each node represents. This is an abstract graph as of now. Each node represents one surface front, right? The location of that node is irrelevant. The track graph computation doesn't care about the location, right? So I do talk about the visual embedding that is primarily to display the graph. So there are many ways to display the graph. One way is to, if you take the surface front, I could use some kind of a centroid of that front to represent the geometric location of that node. Right? It's not ideal, but that's just a quick hack. The algorithm doesn't really focus on the geometric embedding. It just takes an abstract graph and processes it. Any other questions? I'm happy to answer questions, by the way, during the talk. So if there's any, please shout out. Yeah.
So what do you mean by the evolution of the surface?
So as you can see, we will see that in the next video. But these surface fronts, right? So for example, the red front changes over time, right? So the entire high salinity water, if you saw in the overview video, it changed, it moved. So the surface front will also evolve. It will evolve geometrically, it will also evolve topologically, in the sense that it may break into two components. Multiple components could merge. It could develop a hole, right? So all sorts of complex features, which makes tracking difficult, right? So that's what I mean by evolution.
Sir, their parameters are different for this ISO volume and XC boundaries.
The parameters used by the algorithm are different, yes. The ISO volume requires only one parameter, which is the 35 PSU. That's the unit by which we measure salinity. The boundary extraction requires other parameters in terms of neighborhoods and so on. So that's different from the first step. Yes, you're right. Yes.
When you said data set and there were all these numbers, so were they the images of the saline water? Because how do you see salinity? These pictures.
Yeah, that's a very good question. So, especially if I haven't seen an actual image, right? So these are all pseudo colors, right? So the data is available to us where we know that we know the salinity at every grid point, right? So which is also an average, right? So it's an average of the salinity in that 1 kilometer by 1 kilometer ocean parcel, right? So that is mapped to a pseudo color, and that's how we visualize the data, right? So in this case, in the first picture, I use different pseudo colors. Typically, we use blue to red, but depending on in the next video, I will indicate if I have mapped salinity to color, right? In the first world map, the color map was blue towards, I think, green, right? So green represents higher salinity. In the later videos, I will probably just indicate the high salinity water directly. So I won't have a color map, right? So the color is otherwise meaningless, right? So it's just a pseudo color. There was a question here.
Question, but what are we using salinity to measure exactly?
Oh no, it's a deep question, deep in the ocean. So it's so salinity affects many things, right? It affects salinity together with temperature. Plays an important role in the monsoon, right? So it plays an important role in marine life. It plays an important role in other called biogeochemical. So all the entire marine ecosystem depends crucially on the salt content, right? So I don't think I'll be able to answer beyond that. I'm a computer scientist, not an oceanographer. So, yeah. Okay, so right. So what did we find from this? So these were the tracks that we extract. We discussed the algorithm. So what we did further was we did some. Again, there was more processing these tracks. So we have the long tracks. We clustered those tracks to identify tracks which behaved similarly and classified them based on their overall behavior spatially, right? And we identified, for example, 3 different clusters. So this is also well documented in the literature. So George et al., I think many years ago, they are oceanographers. They identify this forking behavior of the high salinity water, where on the left you see the high salinity water going towards the coast of Vishakhapatnam, in the Indian coast. There is another big high salinity water going into the Bay of Bengal, and one more going towards Andaman. Right, so this was already well documented, and we were able to quickly kind of replicate those results, right, with essentially a simple algorithm, right. But we also found a few new things. We found another behavior which is close to the coast, right. We noticed some high salinity water moving along the coast. Now this was interesting, and this led to further studies by the oceanographer on what is called the East Coastal Current, right, and understand its role in the movement of high salinity water, right. So visualization can help. Like I said, it's an exploratory study. It helps identify some phenomena and maybe build hypotheses, and then you test those hypotheses using further studies, right. So that's with the front. This is what we see. So now we are tracking the surface fronts with the isovolume. Right? So what you see on the left is the entire volume. What you see on the right is the surface front as a surface. So the surface rendering, and you also see one track, right? So this probably answers one of your questions about what are the nodes, right? So what you see at the tip of the track is the node. That's right now the centroid. And we are tracking it over time. Notice that there are multiple track components, and we are able to track one of them, right? The color scheme indicates the time for the track, right? So this is one track, and you see this track move towards Visakhapatnam, and we also had a lot of studies on understanding what caused it to move there, right? So we understand that there is an eddy that forms, and that transports the high salinity water towards the coast. Yes, question.
So this visualization is in tandem with the simulation, or simulation is done and then the pattern is discovered?
Oh, the simulation is purely to generate the salinity distribution. So there is what is called an ocean model, right? So RONS is just one ocean model. So this is essentially solving their partial differential equations, right, to solve for temperature, salinity, and so on. So that's what I mean by simulation, right? So that gives you the data, and then you analyze the data that comes from the simulation.
Okay, so then when you say you discovered, that is the data was there?
Yes, the data is there already.
Visualization.
Right. So we don't play any role in simulation. We do only analysis of the data. Yes. Okay. So that leads me to, or at least it led us towards thinking about building visualization systems, right? So this was a specific problem, a specific instance of studying a particular phenomenon in the Bay of Bengal. No matter that the oceanographer spends their entire lifetime studying just this one phenomena, right? Unlike us, who jump from one problem to the other. So we realized we would be interested in generalizing this, right? So can we provide tools and frameworks to support exploration of different variables, different scalar fields, and possibly vector fields for the oceanographer, so that they can study other such phenomena, maybe in the Bay of Bengal or maybe elsewhere. So that led to the development of PyPara Ocean, which is a visualization system that runs on top of a very popular visualization software called ParaView, right? My guess is perhaps there is one or two who have used ParaView. Anyone here heard of ParaView or used it? Probably not. So if not, you can take a look. It's a very powerful visualization software, general purpose. What we developed is PyPara Ocean as a plugin within this system with modules catered to ocean data visualization, both in 2D and in 3D. The benefit being that we allow for an extensible system that rides on the benefits from ParaView, which runs in a cluster, which uses the GPU which uses heterogeneous architectures that are at your disposal, right? All transparently. So we are able to ride on top of that while providing something that is useful and easy to access for the oceanographer. So this is now available for download, so you can try and take a look. Both ParaView and PyParaOcean are available. Right? So I want to spend a little bit time talking about the architecture. Like I said, PyParaOcean sits on top of ParaView. So we built it in this as a 3-layer system, right, which has a client that runs all the processes, that takes care of managing all the processes on the server and sending data, or not sending data, launching new tasks, right, and kind of discarding old tasks and so on. There is a data server which takes care of only data management, right? Processing the data, loading the data, making it available, and so on. And a render server which takes care purely of the rendering or the displaying the data. The benefit of this partition is that we are able to handle large data sizes in the render server without worrying about the data management issues, which are already taken care of by the current solution or any new solution that could come up, right, in future. And the client can be like a small terminal, right? So this is also thanks to ParaView supporting such an architecture, right? So the interface looks like this. A dashboard design is quite important in a visualization system. What you see on the right is the main dashboard, which shows you the visualizations. Here what you see is a view of the entire ocean along the depth with some plots, I'll get into that, that show the profile of a particular variable. For example, in this case, I think this is temperature, I'm not sure, I'm not able to read it. Across depth, x-axis is depth, and the y-axis shows one variable that you can choose. What you see below that is a parallel coordinate plot. This is maybe another takeaway if you want to go and read it up. This is a very useful visualization representation that allows you to look at high dimensional data, 4 to 10 dimensions, right, on the plane without doing any dimensionality reduction. This allows you to look at relationship between points in your high dimensional data set and so on. So it allows for this parallel coordinates plot. All of these are called linked views. So you can select regions in one view and they are automatically identified in the other, right? So this is something that allows you to explore the data really well. Like I said, there is the profile view, there is the parallel coordinates plot, and the volume view, which allows you to show the entire scalar field over the volume. There is a pipeline browser. This is like a network interface that shows what modules you have executed and in what order. There is a properties, which is essentially a UI that allows you to change the parameters. Right? So some modules, just a glimpse of some modules that are supported. Seed points for streamlines. Right? Streamlines allow you to show vector fields. Right? You may have seen this, and you may know what they mean. So these are curves that indicate the behavior of the vector field. Right? So they are integral lines, so that show you how the vector field is moving. Right? And it's very important to seed them appropriately so that you understand. So I can show you 3 examples with 3 different seeding strategies, give you very different pictures. Right? On the left is just uniform. You place seeds everywhere and you trace the path of a particle as it moves along the vector field. Right? But if you seed it such that you want to focus on high turbulent regions, then you capture the the turbulence in the flow, as you see in the middle. And on the right is a very more specialized version of that using a criterion called the Okubo-Weiss criterion. If you want to look at high speed water, then you can seed the points close to the based on the flow magnitude, right? Or based on salinity, if you want to capture the regions with high salt values, right? Path lines are also supported. So these are flow lines of the vector field over time, right? So you seed a massless particle and see what happens to it as it moves with the flow over time, right? So in this case, this is not Bay of Bengal. This is over the Red Sea, right? And it allows you to track these paths over time, right? Eddies are, like I said, big whirlpools. These are also supported in Paipara Ocean. Eddy can be extracted using many ways. Just like a cyclone, the center of the eddy has very low velocity, almost zero, and the boundary of the eddy you have very high velocity, right? And if you detect these minima of velocity, then you capture the center of these eddies, right? But a naive computation will show you all these black dots, which are all local minima, but there's a lot of noise. So you need a systematic way of removing the noise to detect those low flow values, right, that correspond to important or interesting eddies. We do that and use that to seed streamlines. And if you seed streamlines using that, you could look at eddy structures, right, which we will see. All these methods are parallelized and computed in a distributed environment. We did some scalability studies to show near linear behavior for a few number of cores. Of course, this does not hold for larger number of cores, and that is a topic for future work, right? To some extent, there is no parallelism available beyond, in many cases, 60 cores. But in cases where parallelism is available, as in the data is large enough, then we would like to really scale it to a much larger number of cores. Right? So I want to close by talking about a case study on this Bay of Bengal. These are the important currents that play a role in the Bay of Bengal, right? There is this SMC, that's the, anyone heard of this? No, it's called the summer monsoon current, which brings in high salt water from the Arabian Sea through the Indian Ocean to the Bay of Bengal. And you see two eddies. One is this AE, the anticyclonic eddy, right, which is clockwise in the northern hemisphere, and the SLD, the Sri Lankan dome, right? These are important features. The anticyclonic eddy is known to bring a lot of high salinity water into the Bay of Bengal. Right? And we want to understand exactly how, right? Just saying this one sentence is not useful. We want to understand exactly how the anticyclonic eddy brings the salt water, right? And with the streamlines extracted using the methods that I mentioned earlier, and displaying the high salt water the way we talked about earlier, you can see that the anticyclonic eddy is moving westward. Right? And further analysis is required to understand what exactly or when exactly does it form, right? And you see the timelines here. You see that the eddy begins forming late June. I think it forms fully in July, and it hasn't dissipated till the end of July, right? So this video, if you see, runs the whole month of July. We also notice that the anticyclonic eddy changes the temperature. So if you plot the 27 degree isotherm, right? So the 27 degree surface, right, in the ocean, you see that at the point that you see, the needle that you see is where you have the eddy. The surface is 27 degree, right? So anywhere above is warmer water, below is colder water. So as the time progresses, you see that the surface is dipping, which means that the warmer waters are going down, right? So this eddy is pushing down warmer water. So that's an important observation because that also plays a role in the movement of salinity. Eventually the eddy dissipates. So this is in August, and we have a visualization of the eddy with streamlines. And you see that over August it is strong, but it dissipates towards the end of August. Right. So these were all created using PyPara Ocean, and that helps create visualizations of this entire phenomenon, right, of the anticyclonic eddy bringing in salt water. So to summarize, we looked at this challenge of ocean data analysis, where we want to study evolving physical features, which is also a computationally difficult task because the data sizes are large. I did not talk much about that, but that's a big topic in itself. I showed you one figure that indicated the scalability of the algorithms. We introduced some these front-based definitions for features. These integrate geometry and thopology in a neat manner, and we designed parallel and distributed algorithms for computing these fronts and tracking them. And in the process, we were able to make some new observations on the salinity movement, right? And PyPara Ocean kind of grew out of this work and resulted in a visualization system for exploring ocean data. So this is ongoing work. PyPara Ocean is still under development. We are trying to extend this to capture eddies from different data. Somebody mentioned about simulations. We have data also from satellites. We have data from other high resolution measurements like radar. We would like to integrate them to capture eddies at higher resolution and perhaps study more local phenomena. So that's the topic of ongoing work. So with that, I end.
Introducing PyPara Ocean,
hold
a
on.
scalable.
If you can switch off you can just reduce the volume on this.
Introducing PyPara Ocean, a scalable, extensible, 3D ocean data analysis visualization system with various ocean data specific visualization. Field line visualizations with various seeding strategies.
Yes.
Eddy identification.
Thank you for the talk, sir. So I had a question on
Front
the
tracking.
PyPara Ocean
Yes,
plugin.
please.
So
Depth profile
how,
analysis
to what extent
and
can we
more.
use this plugin? Like, is it restricted to the ocean data?
Introducing
or
PyPara
can we as
Ocean,
well use
a
it for other
scalable,
purposes?
extensible,
What
3D
other kind of
ocean data
data?
analysis
We
visualization
meant,
system with various ocean data specific visualization
meant this
modules
for
like
oceanographers, right? And
field
so there
line
are some
visualizations
specific
with various seeding strategies,
modules in there
eddy
that are of use
identification,
for oceanographers typically.
front tracking,
But a lot of the studies by
depth
an
profile
oceanographer is
analysis,
around flow,
and more.
right? So if those characteristics,
Introducing
for
PyPara
example, somebody
Ocean,
who's studying
a scalable,
atmosphere,
extensible,
they may also be
3D
interested in some
ocean
of
data
them,
analysis
but they may
visualization
not
system
use the same
with various
terminology.
ocean data specific
So,
visualization
so in that
modules
sense,
like
I would say
field line
very, very
visualizations
guarded.
with various seeding
Yes,
strategies,
but I would probably
eddy
better off saying
identification,
no, right? That it's primarily meant for
front tracking,
oceanographers. If you want a general purpose visualization
depth
system,
profile
I would recommend
analysis,
ParaView,
and more.
which allows for all these capabilities, but you may have to do a
Introducing
lot of
PyPara
work on your
Ocean,
own
a
to cater
scalable,
it to your
extensible,
dataset.
3D ocean data analysis visualization system with various
So
ocean data
it allows
specific
for data
visualization
in this
modules
NetCDF
like
format. So
field line
NetCDF is actually
visualizations with
used
various
by
seeding
oceanographers,
strategies,
climate scientists,
eddy identification,
geologists, right? Geotechnical
front
engineers.
tracking,
Many people use this.
depth profile analysis,
So if the
and more.
the data will load, right?
Introducing
but some of the
PyPara
modules
Ocean,
may not
a
be
scalable,
meaningful. They
extensible,
will work,
3D
but
ocean data
the
analysis
interpretation is
visualization
where
system with various
things come
ocean
into
data
play, right?
specific
So
visualization modules
a
like
materials
field
or
line
maybe a
visualizations with
geologist
various
would be
seeding
able to load their
strategies,
data in here, but they may not be
eddy
able to use our
identification,
modules to answer their questions.
front tracking, depth profile
Yeah,
analysis,
go ahead.
and more.
The next year.
In eddy identification,
Introducing PyPara-Ocean, a scalable, extensible,
That's a very
3D
good question.
ocean data
So,
analysis visualization
so this is
system
where
with
topology
various
comes in,
ocean data
and I didn't
specific
talk about
visualization
that.
modules
So,
like
these
field line visualizations with
these are
various seeding
minima, right?
strategies,
So these are flow minima.
eddy
So I
identification,
think of them as a
front
scalar field,
tracking,
which is speed,
depth
just the
profile
magnitude of the
analysis,
velocity.
and more.
And I
Introducing
use this
PyPara-Ocean, a
framework called
scalable,
topological
extensible,
persistence,
3D
which
ocean
allows
data
me
analysis
to capture
visualization
the
system
size of
with
each
various ocean
minima
data specific
as
visualization modules
the
like
size of the valley that it
field
represents.
line
So if you
visualizations
think
with
of
various
these
seeding
as
strategies,
like a landscape, right, with lots of
eddy
valleys,
identification,
each valley is represented by a local
front
minimum,
tracking,
right? The smaller valleys,
depth
the
profile
smaller minima are
analysis,
the ones which correspond to
and
small
more.
valleys, which could be embedded inside a bigger
Introducing
valley.
PyPara-Ocean,
So
a
persistence allows
scalable,
me to
extensible, 3D ocean data analysis
kind of
visualization
systematically
system with
recognize
various
which are
ocean
the
data
low
specific visualization modules
valleys
like
and remove them without
field line
affecting the other
visualizations with various
valleys. So
seeding
it doesn't do a
strategies,
smoothing and so on.
eddy
It allows me to
identification,
pick and choose and remove
front
those
tracking,
valleys. Right. So it's a very
depth profile analysis,
simple
and more.
approach, which is also
Introducing PyPara-Ocean,
implemented
a
using
scalable,
by a
extensible,
combinatorial
3D ocean data
method. So it's
analysis
fast.
visualization system
Yeah,
with
but if you
various
want to look
ocean
it up,
data
it's called
specific
topological
visualization
persistence.
modules like
Yes.
line visualizations with various seeding strategies, eddy identification, front tracking, depth profile analysis, and more. Introducing PyPara-Ocean, a scalable, extensible, 3D ocean data analysis visualization system
Yeah, so this
with
is
various
where an
ocean data
interdisciplinary
specific visualization
collaboratory
modules
effort
like
really helps.
field
Right?
line
So
visualizations with various
the
seeding
method does
strategies,
not care, but the
eddy
oceanographer
identification,
tells
front
us
tracking,
what are the boundaries. Right?
depth
For
profile
example, so
analysis,
there is no
and
clear
more.
definition of
Introducing
Bengal because, for
PyPara-Ocean,
example, we
a
also care
scalable,
about what comes in
extensible,
from Indian
3D
Ocean.
ocean data
Right?
analysis
So,
visualization system with various
in
ocean data
my
specific visualization
naive
modules like field
kind
line
of
visualizations with
outlook.
various
So
seeding strategies,
the part of
eddy
the
identification,
part that you see here, I don't know.
front
Yeah,
tracking,
what you see here is essentially
depth
you want
profile
to
analysis,
go into
and
the Bay
more.
of Bengal, into the Indian Ocean, right, and
Introducing
all the way on the
PyPara-Ocean, a
east towards
scalable,
the
extensible,
towards
3D
Andaman.
ocean data
Right. So
analysis
that is our region
visualization
of
system
interest, but
with
the
various
exact
ocean
latitude,
data
longitude
specific visualization
is
modules
provided
like
by the ocean.
field line visualizations with
So
various
I
seeding
don't decide it.
strategies,
That's the answer to your question.
eddy
The oceanographer
identification,
knows where
front
are the
tracking,
broad systems. For example, if you
depth
remember the
profile
schematic,
analysis,
we know
and more.
the high level. At the high level, we know what are the
Introducing
major
PyPara-Ocean, a scalable,
features in this
extensible,
space. We
3D
know the
ocean data
Sama-monsoon current.
analysis
We
visualization
know all the
system
river
with
systems.
various
We
ocean
want
data
to ensure that
specific
they are all
visualization
included,
modules like
right? They are not
field
excluded.
line
But at the same time, we
visualizations
don't
with
want to
various seeding
expand it all the way to
strategies,
get the Arabian Sea
eddy
or
identification,
all the entire
front
Indian
tracking,
Ocean, which will not affect
depth profile
the
analysis,
results. It will just lead to
and
more
more.
computation.
Introducing PyPara-Ocean, a scalable, extensible, 3D ocean data analysis visualization system with various ocean data specific visualization modules like field line visualizations with various
Okay,
seeding
so it's a good question.
strategies,
So
eddy
a couple of them
identification,
are done by
front
under the
tracking,
hood by ParaView, right?
depth
So, for
profile
example,
analysis, and more.
there is something called isovolume
Introducing
extraction,
PyPara-Ocean,
right?
a
Where you want
scalable,
to extract all
extensible,
the
3D ocean data
regions
analysis
which
visualization
have a
system
particular
with various ocean data specific
salinity value,
visualization
right?
modules like
Now, the
field line
parallelization in this case
visualizations with various
happens in
seeding
a data is
strategies,
essentially a data parallel algorithm
eddy
where you
identification,
split the data and send it to the
front
different nodes,
tracking,
and each one does this
depth
on its
profile
own, and then there is a
analysis,
stitching process,
and more.
right? So the way this is
Introducing
a very simple data
PyPara-Ocean,
parallel
a
algorithm.
scalable,
What makes it
extensible,
difficult
3D
is
ocean
the
data analysis
communication,
visualization
right? So
system
bringing in
with various
the
ocean
data,
data
the
specific
result back
visualization
together,
modules like
and something
field
that
line
we
visualizations
did
with various seeding
to
strategies,
improve the
eddy
runtime is to
identification,
introduce a new way of
front
partitioning
tracking,
the volume
depth
to
profile analysis, and
I don't know
more.
if you know what ghost cells are. Ghost cells are these
Introducing
buffer cells
PyPara-Ocean,
that
a
you add to the
scalable,
boundary of a
extensible,
block
3D
that allows for
ocean data
communication
analysis
to the
visualization
neighboring
system
block.
with various ocean data
so
specific
that
visualization modules like
so the ghost cells are
field
kind
line
of shared by
visualizations with
two
various
neighboring
seeding
blocks.
strategies,
So that's where you can store
AD
everything and you can
identification,
kind of send it to the neighboring
front
block.
tracking,
So we introduced a new
depth
way of
profile
partitioning
analysis,
these
and
blocks,
more.
partitioning the data into these blocks such that
Introducing
the
PyPara
communication
Ocean, a
is
scalable,
reduced,
extensible, 3D
the
ocean data
load
analysis
balancing is
visualization
as
system
high as
with various
possible,
ocean data specific
while
visualization modules like
potentially increasing the number of
field
ghost
line
cells.
visualizations
A
with
lot of
various seeding
existing algorithms
strategies,
try to minimize the number
AD
of ghost cells,
identification,
but we found out that that
front
may
tracking,
not necessarily be
depth
crucial.
profile
So this is in case
analysis,
you know the details,
and more.
but if you don't know,
Introducing
then
PyPara Ocean,
the high
a
level algorithm is
scalable,
a data parallel
extensible,
algorithm where you
3D
take the
ocean
data,
data analysis
partition it into
visualization
smaller
system
blocks,
with various
send it
ocean
to
data
different
specific
nodes for
visualization
processing,
modules like
and then you have a second phase
field
where
line
you stitch all of them
visualizations
together.
with various seeding
So that's the
strategies,
approach.
AD identification,
Is this MPI?
front tracking,
Yes, so this is MPI. So all this was
depth
implemented in
profile
MPI,
analysis, and more.
and I think the experiments here
Introducing
were on
PyPara
an
Ocean,
AMD.
a scalable,
I think this was
extensible,
with,
3D
if I
ocean
recall,
data
8
analysis
nodes.
visualization
Each one had
system
about
with
32
various ocean data
cores each.
specific visualization modules like
Yeah, so it is
field line visualizations with various
Sir, I
seeding
have a question.
strategies,
What about the
AD
capture
identification,
What are the type of input images used?
front
Is
tracking,
it only the satellite images which are
depth
in
profile
one space or
analysis,
thermal images?
and more.
Okay, so
Introducing
the
PyPara
data that
Ocean,
I'm
a
handling
scalable,
here, I talked
extensible,
about 3 different
3D
data
ocean
sets.
data
All
analysis
3
visualization
NEMO,
system with
Gloris,
various
and
ocean data
ROMs.
specific
They are all
visualization
simulation data,
modules like
right? So these are data
field
that
line
come from
visualizations with various seeding strategies,
solving, like I said, these
AD
PDs
identification,
to get
front tracking,
to get the
depth
salinity,
profile
temperature,
analysis,
velocity, and so on.
and more.
So there is no; these are not imaging data. They're not
Introducing
from satellite
PyPara
imagery,
Ocean, a scalable,
but they
extensible,
are
3D ocean data
technically they are called
analysis visualization
reanalysis
system
products,
with
right?
various
So a
ocean data
reanalysis
specific
product is one where
visualization
you run a
modules
simulation,
like
but you correct it
field line
by getting
visualizations with various
actual
seeding
measured data,
strategies,
right? So it could be from
AD
satellite measurements,
identification,
it could be from floats.
front
For the
tracking,
ocean, you have floats all over, and that
depth
gives you
profile
actual data.
analysis,
That will
and
correct your
more.
simulation periodically.
Introducing
So
PyPara Ocean,
these
a scalable,
simulation products, they are
extensible,
called
3D
reanalysis
ocean
products.
data analysis
So the data
visualization
are from
system
reanalysis
with
products.
various ocean data specific visualization
How does one
modules like
identify the lower high
field
salinity?
line
Is
visualizations
it
with
something
various
that is
seeding
separately
strategies,
provided to you by the oceanographer,
AD
or is it something that you
identification,
calculate on your simulation?
front
Right. So
tracking,
the threshold of 35
depth profile
tells me
analysis,
which is high
and more.
salinity, and why 35? Because that's the average
Introducing
salinity
PyPara
of the
Ocean,
ocean.
a scalable, extensible,
Does the
3D
color
ocean data
change
analysis
depending on
visualization
the
system with various ocean data specific
No, I think the
visualization
color
modules
depends on
like
many other things,
field line visualizations with
not
various
just
seeding
the salinity.
strategies,
This is this Raman
AD
effect, so
identification,
it's a little bit more than
front
just
tracking,
salinity. So it depends on
depth profile
the
analysis,
color as we see it,
and more.
if that's what you mean, right? The color of the water
Introducing
as we see it,
PyPara
if it goes
Ocean,
from
a
green towards
scalable,
blue. I think
extensible,
it's a
3D
combination of
ocean data
the
analysis
atmosphere,
visualization
the
system
depth
with
of the
various
ocean,
ocean
and so
data
on.
specific visualization modules like
Okay, so I
field
know there
line
are many questions,
visualizations with
so that's
various
why
seeding
we have
strategies,
preponed the break to
AD
now and
identification,
ask the questions in the break. So we'll have coffee
front
break after
tracking,
now. So let's thanks Vijay
depth
for
profile
this wonderful
analysis,
talk.
Thank you. Thank you.
and more.
10:30.
So we have oh, thank you. Thank you. Okay, so we'll break for coffee now, and please gather back at 10:50. Okay, thank you. culminating in the development of the frontier supercomputer, the world's first exascale supercomputer. Arka was awarded the Shanti Swarup Bhatnagar Prize this year. It's very recently. He was inducted into the Micro Hall of Fame in 2024. He received the Intel Rising Star Award in 2021 and Google Faculty Awards in 2021 and 2023. Over to you, Arka.
Thanks for the introduction. Can you hear me? Can you turn off the slides? Okay, so can you all hear me? Okay, so today we'll be talking about the software, the GPU software. GPU stands here for Graphics Processing Unit, but we will be talking about the computing that actually happens on the GPU. Okay, so the first obvious question is that why care about the GPU and the software running on it? Okay, so this should not be any news to you that like we are generating a lot of data, right? Every time you click a like button, you buy something on Amazon, there is a piece of data that you are generating, and there is you can get actionable knowledge out of it. For example, that can help in advertisement and so on. But to extract an actionable knowledge out of a data, you require a lot of compute, and that compute also needs to be fast enough or parallel enough, because the actionable knowledge that you can get out of a data also has an expiry time. Like if it is too late, then it is no more useful. Okay. And in this context, the GPUs come in. So they are essentially used as an accelerator for parallel computing. And you can actually find use cases all over the place. I mean, of course, machine learning, AI, ML, but beyond that, like all the HPC systems, if you look at there are top 10 supercomputers today, 9 of them primarily rely on GPUs for their compute power. Graph processing, databases, data warehousing, everywhere you'll actually find GPUs as the primary computing element. Since it has become such an important part of the computing stack, the quality of the software that actually runs on the GPU is very important too, right? So now what we'll actually define is that what I mean by that, the term quality. Okay, so by that, the quality of the software, we mean two things. Okay, so the first one is that if I'm running a program, it should not be the case that out of 100 times that I actually run, 99 times it gives you the right result, but one time it fails. That is not acceptable, because one time it fails, it can actually cause a disaster. For example, this happens often. If you have followed the news, like I think the last month there was a huge outage on AWS, and if you look at what really happened, it will almost always boil down to not the hardware failure, but the software bugs, right? For example, in that case, what happened is that there was a DNS automation software that was actually that would actually automatically create entries for the DNS to do a load balancing. That actually created a null entry. That is it. And then everything from, say, banks down to even this, smart beds, all fail. Okay, so because a lot of our life today depend on the software. So if it fails, even in a corner case, it's a disaster. And this is not only the case. There's a lot of big outages keep on happening. There was one, I think last year or early this year, that is because of there was a blue screen of drift on Windows software, and then the flights and everything got cancelled and so on, because there was again an buggy software update, right? And there are other things like Facebook also had something similar, Google had something similar. So what I'm actually trying to get at is that if there is an outage or the software bug gets into the production software, right? Even if it is a very corner case, when it actually gets triggered, if it gets triggered, it causes havoc. So the quality of the software is important, and the fact that a lot of software today uses GPUs the software that the quality, the reliability of the software that is actually running on the programs that are running on the GPU matters to our daily lives. So that's one part of it. One part of what I mean by quality of the software. The second part is, which we'll be talking about, is how efficiently that software is using the GPU hardware, because the GPUs are extremely costly. If you want to actually buy a top end GPUs today, it will easily cost like a piece would be like more than $20,000 US. That's a lot of money, and a lot of companies actually buys a lot of them, like 100,000, 200, 300,000 GPUs and so on. And this year, the estimate is this year. The estimate is that all these big companies, the software companies, they're spending more than $455 billion just to for the data centers, and most of that money goes to NVIDIA or the GPUs. Okay, not only that, but also there's a significant fraction of the energy consumption. So what this graph is actually showing is that it is projected that by 2030, around 12% of all electricity consumption in US will be due to data centers. So what it means is that the cost of compute is really high, both in terms of the GPUs that you are procuring, but also their running costs, the energy. So when you have a very costly hardware, you want to actually utilize it well. Otherwise, if you are underutilizing it by say even 20%, which means that you roughly would require 20% more number of hardware. So that's actually a real dollars, right? So what it means is that we want to make sure this second part, which is it's going back. We want to actually make sure that the software that actually uses this hardware uses it well. Okay, so these are the two aspects that we'll be talking about, and this is the two parts that actually, when I talk about the quality of the GPU software, these are the two things that I actually mean by that. Okay, so the other thing for this talk, if you have any clarification question, please feel free to actually, interrupt, and I'll actually answer that question. A lot of this material I'll also use is kind of would not only the research part, there will be parts that will actually go deep and will be a research part, but I also I would not assume that you know about GPUs, so I'll use it also as a teaching material. Okay, so if you have any question, please feel free to interrupt. Now, those who haven't looked into the GPUs much, you might have this question, right? So the GPUs, as its name suggests, it's a graphics processing unit, right? So how come that you actually started using it for parallel computing, right? So that's the first question that we will actually try to answer. So as we discussed, GPUs were originally designed for graphics processing. And when you talk about graphics, what it is really processing, right? It's processing images, right? That's, even if the video is just nothing but a stream of images. Okay. And if you think about images, what they are actually pixels. So this is typically a two-dimensional matrix of pixels, right? So what the GPUs were designed to do well is you are doing identical operation in parallel on each of these pixels, right? And then come around 2007, 2008, credit to NVIDIA, they realized that this kind of computing pattern is also pretty good to operate on matrices like linear algebra operations, right? So because instead of thinking about the pixels, you can think of it as just a number, data items. As soon as that happens, the picture becomes an matrix. And then serendipitously, what happened is that when this ML AI thing actually happened, these were all linear algebra operations, mostly. It's all matrix operations, right? And here you go, this is the kind of the operations that the GPUs are really good at, because it can do a lot of identical parallel operation, not on the pixels, but on the data items, right? So of course, I'm actually, oversimplifying what the GPU does, but that's the crux of it, like how GPUs became the accelerator of choice for parallel computing. It has a lot of tricks up the sleeve. For example, the basic programming model that it has, the execution model it has, is a single instruction, multiple data, which is very efficient when you are actually operating on same operation you are doing on multiple data items. There also, it keeps a lot of threads that are ready to actually run. Doesn't require operating system to do the context switching. It also has a very efficient memory subsystem where it actually looks for opportunities where multiple memory accesses that are actually happening at the same time, whether they can actually zap it into a single lookup. It also have very high bandwidth memory, like if you compare it to the CPUs, and at the top end of the CPUs you typically get a memory bandwidth of say 400 or 500 gigabyte per second, while at the top end of the GPUs today you will easily get 8 terabyte per second of bandwidth. Okay, so that is about the background why the GPUs are becoming or has become an accelerator of choice for parallel computing. Any questions so far? Yes, go ahead. What's your name?
Nimra.
Okay, go ahead.
Sir, these numbers are images.
These are numbers, these are matrices. Yes.
Okay, so it is some representation of the image.
No. So the point I was actually trying to tell is that originally GPUs were designed to process images, which was nothing but, like I say, a 2D matrix of pixels, right? Then, NVIDIA really realized that the same structure of compute you can actually do on matrices. If you start thinking not instead in terms of pixels but in terms of data items, because if you now it looks a picture looks like an matrix, a two-dimensional matrix. So the point is that the same computing structure that actually works well for graphics works well for data parallel operations, data parallel computation. That's the reason the GPUs really picked up for parallel computing. Does it make sense?
Yes.
So the way I'm trying to answer the question that all the GPU's name still has this graphics processing unit, but you are not using it, the purpose that I'm actually talking about, you're not using it for graphics but for data parallel computing, which is all over the place for AI ML.
So,
Yeah.
like the follow-up question would be really unrelated then, because I was just trying to make sense.
Then don't ask unrelated questions. That's important. Okay. Yeah. Okay. So this is the reason why we actually all so much of software actually runs on the GPU today. Okay. So with that kind of background, we'll now start getting into the first thing that we talked about, right? Like the first part of the quality of the software, where we will talk about how hard it can become to write a correct GPU software. Okay. So we'll try to actually motivate that and why it becomes so hard. Okay. Now we'll actually get down a little bit into the details. Some of you might get lost. That's okay. I'll bring it back again. It's okay not to understand everything. It is perfectly fine. Okay. So the type of thing that we'll actually look into here, bugs that actually occur sometimes, and those are the most hard and most critical software bugs to detect, because if there is an say segmentation fault that was happening, then that would of course get fixed before the software is shipped to the customer, right? If a particular bug occurs often enough under some input, that will of course get caught during the software testing. We are not talking about software that you are submitting for program that you are writing for your project, right? We are talking about production grade software. So they go through a significant software testing. So what is even after that, what is hard to catch is that the bugs that are seldom occurs, rarely occurs. But the problem is if they go down in the production software, you are in trouble. Okay, so that is the kind of thing that we will be talking about. We will be talking about in terms of synchronization bugs. Okay. So now to understand the scale of the problem, we need to also understand the scale of parallelism in GPUs. GPUs are not another very large multi-cores. It's of a very different scale. So on the x-axis are the years, these names that you actually see, these are the NVIDIA's, the GPU architecture that was actually launched that year. Okay, so on the y-axis, you have the number of concurrent threads that a given GPU, a single GPU, can have active or ready to run at any given point of time. So we are talking about around, say, 200 to 300,000 concurrent threads, the GPU threads that are ready to run at any point of time in a single GPU. Yes, go ahead. What's your name?
Mohit,
Yes, Mohit.
what's the difference between RTX GPU and AI GPU? Because like
Okay, don't ask irrelevant question. Okay, we'll come to that later. Focus on what I'm trying to teach. Don't ask like RTX and so on. If you want to actually know about it, and catch me after the talk. Okay. Okay. So any other question? Okay. So what happens is that whenever you have a lot of parallelism, right, and you have to manage that parallelism, you need an hierarchy. For example, if you have a lot of students in a class, you will have a hierarchy of instructor. Sometimes there is a faculty, then there is an instructor, then there is a TA, and so on. What they are trying to do, they are trying to divide the work or amount of parallel operations that each of them has to actually handle. So exactly the same thing actually happens inside a GPU. The whole architecture is organized in a hierarchy. Okay. So if you open up a GPU, what the unit of a GPU that you will actually find is, in NVIDIA's term, it is called a streaming multiprocessor. AMD would call it a compute unit. Okay. Broadly think of these are actually just a core of a multi-core. Okay. Not exactly, but for now that is good enough to understand. So you will have a multiple streaming multiprocessor in a given GPU. Typically you would have, just to give you an feel of the number, you will have say 108 SMs in a given GPU. It depends on what type of GPUs you are buying. Okay, so to answer your question, for example, the number of SMs will actually change based on, like, if it is an RTX GPU, it will be very less. If it is a server class GPU, then you will have actually many more number of them. Okay. Now, if you open up these SMs, what you will find is internally that the basic unit of execution is the single instruction multiple data units. These are actually vector units that can actually execute same instruction but on different data elements. That's the core of how GPU gets efficiency in parallel computing. And then there is a bunch of memory, level 1 cache with each single unit SM, and there is some kind of a scratchpad software. It's a software managed cache. You don't have to worry about that here. And then there is some shared memory as well. Okay. Now, the way that you actually program these GPUs also reflect this hierarchy of the hardware in the programming in a thread hierarchy. So by that, what I mean, so there is a group of threads, typically called the WOP. Typically, there will be 32 of those threads. They execute or try to execute in a lockstep. Okay, same instruction or different data, and those actually map to a single SIMD core. Okay, then you have around a group of 1024 up to 1024 threads called a thread block. Okay, in AMD terminology, it will be a work group. Okay, that are actually scheduled on a single SM that we talked about, right? Like streaming multiprocessor. And then the way that you actually launch and GPU kernel or you write the program is that you specify in the program what each thread would do, and then mention how many threads, GPU threads, you want to launch that will execute the same program. So that's called the grid. And typically you will have hundreds and thousands of threads, which means that you have thousands of thread blocks. So this is the hierarchy. Now, whenever you have parallel programming, you need to synchronize from time to time, because that's how the basic nature of parallel programming, right? And synchronizing across these hundreds and thousands of threads globally is very costly. So because more number of threads, harder it is to actually synchronize efficiently. And the way the GPUs are programmed, in synchronizing across so many threads are also programmatically not necessary always. So the GPUs actually, the hardware actually provides, and this is unique to GPU programming, you would not have in the CPUs, is something called scope synchronization. What it means is that you are allowed to synchronize within a subset of threads, not all. Okay. For example, there is something called a block scope of a synchronization operation. So synchronization operation could be an atomic operation, a fence operations, and so on. So I'm assuming that by this time you know what those atomic or fence operations is. If not, you can actually ask me. I'll explain along the way. Okay. So what it means is that if you have a block scope operation, then the effect of that synchronization operation would impact only the threads that are part of the same thread block. Say the group of up to 1024 threads. If you want to actually synchronize across all the threads, then you have to use something called a device scope synchronization. Okay. Now, why it actually matters? Why this different kind of thing? This is a more of a trade-off with the performance, because what really happens is that if you are synchronizing, sorry, not this one. If you are synchronizing across all the threads, then that synchronization operation is much more slower than if you actually want to synchronize within only a single block of threads. Okay, so that's obvious because less number of threads that you have to synchronize for. Now I'll actually show with a kind of a pictorial example what is this performance and so the programmability challenges that comes up with the scope synchronization. So let's take an example, pictorial example. So here, this blue thread is a producer thread, and the red thread is a consumer thread. Like you are communicating some data, so you are trying to actually synchronize. So that's the assumption. Okay. So so let us assume that these two threads are part of the same thread block. If that actually happens, then all those threads will be actually running or will be scheduled to run on the same SM or the same symmetric multiprocessor. What it means is that they share a bunch of shared resources like L1 cache and the scratchpad and so on, right? So now if these two threads, producer and consumer, happens to be part of the same thread block, and if they use say device scope synchronization, then what would happen is that this producer thread will actually push the data that it is producing up to the shared label to cache, and then the consumer will actually bring it from the label to cache, right? However, given that this blue and the orange threads are part of the same thread block, this is wastage of work. They could have actually used a block scope and write it to just the L1 cache, which is shared between these two threads, and get the data from there. That would be much more faster. Okay, how much faster? So it could be at 21 times faster. And this is, we are talking about the real hardware numbers. Faster to actually just communicate through the shared level 1 cache versus communicate through an level 2 cache. Okay, so there is a lot of performance incentive to use this block scope operation versus a more wider scope or broader device scope operations. However, the problem is that it also introduces a chance of programming error, which we'll call a data race. So what can happen is that now assume this producer and the consumer threads are part of different thread blocks, which means that they may sometimes can get scheduled on different SMs. Not always, but sometimes. Okay. And if that happens, and if you still use a block scope operation, synchronization, even if the producer actually consumer uses a device scope, you would not get the up-to-date data. So which means that you can actually get a functional correctness, programming error. Okay. So that's called a data race situation, where you are not synchronizing the properly. So you can see there are performance versus programmability trade-off. You might actually get performance by using smaller scopes of the synchronization, but that can actually potentially lead to bugs in the program. Yes, go ahead.
Sir, whatever is part of L1, isn't that automatic? Just asking, isn't that automatically a part of L2 and the bigger memory, or is it that if it goes to L1, it stays in L1 only, it is not updated in L2?
Yeah, very good question. So what's your name?
Jayan Jha.
Okay, yeah. So in case of GPUs, the level 1 cache is not kept coded by the hardware. So if it is pushed only written in the L1 cache, the other threads running on the another SM doesn't see the updated data unless the software explicitly asks for it. And the software's way of explicitly asking for it is synchronization. If it doesn't does the synchronization properly, then it will not see the updated data. Does that answer your question?
Yes, sir.
Okay. And what we'll actually show is that next, actually running. What is the when do we start?
So I have 20 more.
20 more. Okay, we'll actually go faster. So I'll let you teach less. Okay. What happened? What I was actually trying to say is that this kind of a synchronization bugs can be actually pretty subtle. If you know of like these operations like a graph coloring, where you have a very large graph, they have actually a lot of implementation or or applications in terms of, for example, in deciding the scheduling, deciding the network, bandwidth or the frequency allocations and so on. So what you are looking at is that you have a very large graph. Think of it as a millions of nodes, and then you have to assign each graph, each node, an unique color such that none of its neighbor has the same color. Okay, so this is kind of a very common problem. So the way that you will actually do that in the GPU is that you will actually break the number of vertices to color into actually groups and assign a set of such vertices to each thread block in your kernel to actually operate on them locally, so that you don't actually synchronize too often. Okay. However, you also want actually load balance. It can happen based on the graph structure that some of the thread blocks, whatever the set of vertices it got, it could quickly finish off its work, but the others are still working. So at that time, you don't want to keep your GPU idle. So you want to do something called a work stealing, where if someone, a thread block, a group of threads finds that its set of vertices that it has to color is already done, it will steal from other queues and other thread blocks work. Okay. So what you have to think of, these are the queues. There are two, thread blocks that are actually operating on this queue of vertices, and it can actually happen that this particular thread block actually finishes all its work quickly. Okay. So since it is actually working on its own local queues, the thread blocks, it can use a block scope operation. Okay, because the other thread block doesn't need to know about what it is doing. But when it actually starts stealing, it's obvious that it's stealing from another thread block's data, so it should use the device scope. However, even in that case, there is actually a risk. The reason is it might happen sometime, unluckily, at the time that one thread block is stealing from a thread, say a thread block is in a queue, that at the same time that the owner of that queue is also trying to take another work item from its queue. If that actually happens, unluckily, then you have a race condition where the updates that it is actually doing, this local thread is doing to this local thread is doing its local queue would not be visible to the thread block that is actually stealing the work. So you would not actually get the same work might be assigned to multiple thread blocks. So that's a data race, a synchronization problem. Okay. So the point of this slide is that many of these bugs can be pretty subtle. Okay. And there are actually more to it. I will not actually have time to actually go over it, so I'll actually skip some part of it. But what is actually goes on is that every time CUDA is a language in which you program the GPUs, NVIDIA GPUs, and every time the new version of CUDA comes up, typically they will actually introduce different types of synchronization, and that actually creates more and more opportunities of different bugs to actually seep in the program. Okay, so I'll skip this part. Like there were other types of bugs that we found out due to different technologies like independent thread scheduling, cooperative bugs, and so on. So this is a paper that was published in the SOSP, that is the operating system conference. So you can actually find the link later. But the whole point is that this particular bug that we actually found out was very interesting, where the software, the programs that were actually, so they, NVIDIA introduced a new feature called independent thread scheduling from the Volt architecture, which was around 2017-18. Okay, the same program that was actually running all fine on the older generation GPUs suddenly will start actually failing in the newer generation GPUs. This is actually deadly, right? You don't expect this. Like you get, something that was running fine, you just upgrade your hardware, and sometimes your software starts failing. So this was actually started happening, and so we pointed this out. I'm not getting into the details of this, but I'll actually make the slides available, but we'll skip this. Okay, but what really actually happened? So once we actually detected this different kind of bugs can actually happen in the GPU software. We found out like many types of this. These are actually synchronization bugs, which means like sometimes they actually show up. Most of the time they would not. What we actually did is that we created an software tool. This is a binary instrumentation tool, which we call the iGuard. So it will actually automatically detect such bugs in the software. So this is a software tool to detect bug in the GPU programs or the CUDA programs, to be very specific. Okay. So the how at a very high level how it actually works, it will actually take a program, it will actually instrument it on the CPU. So these red lines are actually instrumented program, and then it will actually run on the GPU. Okay. Along with this, blue one is the actual program, and then this red one you can think of the checkered program that runs along. It skips a bunch of metadata and so on, and then it will actually find. It will have a race detection logic. It will find out if there is the potential of races that might be actually happening in this program. There is a set of rules. Of course, intentionally this is the fonts are small so that you don't have to read. But ladies and if you are interested, the paper is of course there. So it will actually find those races, and ultimately the important thing is that it will actually tell the programmer that why exactly this different kind of bugs, the functional bugs that might be actually happening in the program. Okay. So then the programmer can actually go ahead and actually fix this program. Yes.
So what's the overhead of the?
Yes, this can be actually pretty high. It could be like 6, 7x, 8x, and so on. But this is a debugging tool. So for example, if for example, this is kind of a Valgrind kind of thing. This is not production. You are actually deploying all the time. This is mostly happening before in the testing and debugging phase.
During development.
Yes. So, and then a lot goes on in designing the software. I'm not getting into the details of that, but ultimately what we actually achieved. So what we achieved is that in a bunch of bugs that were not known previously, that were there in the software, including in NVIDIA's own libraries like QML and CUB and CG and so on, there are actually bugs which are also was acknowledged by them as well, and this software is open source. Anybody can go ahead and actually try using it. I skipped a lot of details, but at a high level, we are trying to actually catch race conditions in the GPU programs. Any question?
Sir, what
Yes.
if two or more thread blocks get idle at same time?
Sorry.
So what if two or more thread blocks get idle at same time?
Added.
Ideal at the same time.
Okay.
It's no process, no thread block are running on them, and the older one is means they are using the same thread block, and they are trying to stealing the older one threads.
I'm confused. Okay. So say it again. I'm not understanding the question.
So means two or more thread blocks gets idle at the same time.
Idle. Okay.
And they are stealing the threads of older one. So.
Okay. So there is what you're saying is that two thread blocks are actually trying to steal from the same. And so that's if it is a program is correctly synchronized, then they will actually get serialized. What happens when you do a synchronization? So it's mutual exclusion, which means like you will actually serialize those operations. So you will take one of the thread blocks, will actually take its work out of the queue first. Other thread blocks will actually take its work out of the queue later, right? Not at the same time. So that will, if it is correctly programmed, then it will actually work all fine. Okay. Any other question? Yes, go ahead.
So in the graph color problem, is the GPU trying to go through all the possible methods of coloring and trying to say that this is valid, this is invalid, or how is it?
No. So that depends. So this is just you are implementing the graph coloring algorithm on the GPU. then the way that you're actually implementing is that there will be each thread will be responsible for coloring one vertex, and then you have a block of threads, which is like thread block. There will be initially, before anything work starts, there will be a distribution of work. So each thread will be said that these are the set of thread vertices you should actually be coloring. You do this kind of partition because you don't want to synchronize across all the threads every time you color an node, because then there will be too much of communication. The program performance will be pretty bad. At the same time, if you do this static partitioning, because of the graph structure, some of the thread blocks might actually finish its work fast. At that time, you don't want to actually keep them idle, because then you are actually underutilizing the GPU. So then they will actually start stealing. As soon as you start stealing, all this synchronization problem actually show up, because then you are actually communicating across the different groups of threads. Okay, so that's what's actually happening. There are other kind of things that I mentioned, independent thread scheduling and so on, which is slightly different, but of the same nature. Like they can happen sometimes. Okay, so this is something that we actually worked on. Is the synchronization errors are not the only type of error these days. We are also looking into memory safety bugs, where for things like, for example, if you have out of bound accesses, like you have a size of an array and you are actually accessing some memory that is actually not within that array bound. This can happen because just like C, CUDA is actually a dialect of C, which means that it also does pointer arithmetic. As soon as you do that, it's not memory safe, right? And if you have this memory safety bugs, this can be also exploited for security vulnerabilities, because you can do code injection and stuff like that. You can steal data as well. And Google has a nice report, and they showed that for over last 10 years of bug reports that they actually analyzed, and found that 40% of the error, this is on the CPU side, but 40% of the memory errors are due to out of bound accesses, even after years of research. So what we are actually working in is looking into how this actually affects the GPU programs, not the CPU programs. Okay, so with that, so the purpose of this slide was to say is that synchronization errors are not the only type of functional errors that you actually have on the GPU program. You also have the memory safety bugs as well. How much time left? 7 more minutes. Okay, super fast then. Okay. It's okay. You don't need to actually understand all the details. It's important to understand what, at a high level, what we are actually up to. The second problem that we actually talked about is the performance bugs. So what is the performance bugs? Here, the program is functionally correct. What it means is that it is doing the computation it is supposed to do. No problem with that. However, it is not doing the computation most efficient manner. So which means that if it should take, like, say 5 seconds, it is probably taking 7 seconds to run, because the program is not written efficiently. Okay, and this is very important. The reason is the GPUs are super costly, but they are also very underutilized. So what this is graph from an Alibaba. If you know about the Alibaba, they are a big Chinese cloud vendor, okay, like AWS and so on. So on the x-axis shows the GPU's utilization. You want almost near 100% utilization. On the y-axis is CDF. I hope you know what is a cumulative distribution function, right? So what it means is that if you look at this graph, what it's really telling you is that nearly 80% of their GPUs, we are talking about hundreds and thousands of GPUs, are utilized less than 50% of its capacity. So that's a lot of wastage in terms of money, because you are now having to buy so many more GPUs, and also in terms of energy, right? And this is not on Alibaba. Microsoft also, Azure also published some data last year where they actually talked about how their GPUs are also typically utilized less than 50% of the time. So what we found is that one of the reasons why the GPUs are underutilized is because the GPU programs that are out in the wild, they are often over synchronized. So what I mean by that, this is just the other side of the data races that we talked about. If you are doing too less of a synchronization, you have this synchronization bugs where the producer and the consumer of a data item, they are not reading the right values.
Sir, is it possible because...
Let me finish. And then it's just the opposite can actually happen when you do over synchronization, which means like you do synchronization more than what you actually needed. That then becomes a performance over it. Now the question.
Is it possible because at a large scale, program and the become more complex, so for the human it's hard to utilize.
Yes, that's the reason. Basically what happens is that in a human mind, okay, fine, 5 minutes there, okay. So you always prioritize functional correctness over performance. Because the programmers who are writing this program, they also know that there is a chance of a data rest and the programs can fail then intermittently. That's a disaster. They would rather say like, let me write the correct program. If you leave some of the performance on the table, it's still quote unquote okay. But in a grand scheme of things, that 10% could be if you accumulate over so many GPUs, it can be actually a lot, right? So what we discovered, this is for the first time we actually showed that the such over-synchronization can happen, and there are many reasons for it. For example, again, like this scope thing that we talked about, the default scope of an operation is always the wider scope, which is the all the threads will actually synchronize. If you want to actually utilize for performance, then you have to actually explicitly change the program to use a scope qualifiers. There are other reasons. Again, I had actually an examples. I will not actually go into that. The example was there to show how subtle those synchronization, over synchronization bugs could be, depending on even, for example, how you define a variable. Okay. For example, whether you define some data as a volatile or not depends whether how much synchronization, what kind of synchronization you would actually require. There are other examples. Again, we don't have actually time. So I'll actually skip that, but overall, the point that I want actually, trying to get at is that what you are saying, that manually finding this unnecessary synchronization is hard. What you require is an automated tool, and that's what we actually built for the first time. That there was a software tool that again, first contribution was that we found like different types of over synchronization that can happen in CUDA programs, and then we actually created a software tool that would actually, that we named this, scope advice that will actually catch those over synchronization. So this was also another useful thing, because what people can actually now do is that don't worry about writing the most performant, most code with the least amount of synchronization anymore. You can just write a functionally correct program and then run it through our tool, and it will then tell you like why you are actually leaving the performance on the table. So that becomes actually easier for the programmer. Again, this is also an open source tool, so anybody can actually use it. I'm not getting into the details of how, what were our, secret sauce. So it's saying 2 minutes. So I can actually run, I'm not getting into all these details. The slide will be with you. You can actually upload it. But the meta point is that how you actually leave so much performance on the table. Okay, this is also, you require a tool to actually detect it, because otherwise humanly it is very hard to detect these performance bugs. Anyway, again, what this one is showing is that this is really useful. There are, like you would actually expect, the NVIDIA, we target NVIDIA's libraries because they are widely used, and we find that this kind of over-synchronization is also there in the programs that are written by their ninja programmers. Okay. And it can actually give you a lot of performance improvement without breaking the program, just by removing some 1 or 2 lines of extra over-synchronization. So with that, just as I mentioned, looking ahead, we are also looking into things where in our lab, where we look into the fact that in a lot of the hardware improvement these days, you can't, because the transistor technology scaling, you can't actually just increase the frequency or have the large caches and things like that. So a lot of performance features that come out, they require software enablement, which means that the software needs to use them right. At the same time, these days, we write the program at a much higher level in using libraries like PyTorch and so on. So there is a semantic gap. So we try to work on this compiler and so on to actually bridge this semantic gap for the GPU programs. So with that, I'll finish this work with this meta point that I hope you appreciate that the quality of the GPU software matters. And when I talk about quality, it is both the correctness, the reliability of it. Now, if it is running 100 times, each time it should actually produce the right result, not the 99 times. And the second is that it also should run as efficient as possible, right? So that's which means that it should not have actually performance bugs. So that's what one of the things that we in our lab work on, and all of the things that I actually talked about is I'm just talking here because my students who are part of this our computer systems lab at IISc who do the real work while I actually come and give Jan. Okay, with that, over to you guys. If you have any question, please feel free to ask.
Thanks, Sarkar. Thanks, Sarkar, for distributing the GAN. Let's take questions.
So this again, I'm just trying to understand. Like in the first case, you were trying to talk about under synchronization.
Exactly.
And in the second case, you were trying to talk about over synchronization.
Exactly.
Now the thing is, I'm still not able to understand how do you find what is the right kind of synchronization, because doesn't that become very much task dependent, that if I'm trying to perform this task, for it this much synchronization is required. So what I'm trying to ask is, then is general purpose GPU even possible? Otherwise
it is, you can actually find it out based on what the program is trying to do. For example, you can actually analyze the program. There, you also know that say CUDA's programming semantics, right? There is a guarantee which is particular different, say a thread fence operation would actually do, and then you actually see that okay, there are say two operations they're actually trying to do, which say one of them is encompassing the semantics of the other operation. So then you know that this other operation is actually redundant, or you can actually see that there is no way that they are actually using a scope that is say a device scope, but you see in the program as you analyze the program that there is no way these two threads can be on two different thread blocks. Then there is no chance that you would actually require this device scope, which is a wide scope synchronization operation. You can actually get by with a much faster block scope synchronization. So you can actually find this by running through the program.
So that's what I was trying to ask. Is it possible to ever design a universal GPU like which can run?
We do not actually design the hardware. We look for only the programs and analyze the programs.
Right. From software perspective.
It's the software perspective. Yes.
From software perspective also, I'm trying to understand if it is possible to design something which can run which can do all type of tasks, universal sort of setting, because then what you're saying becomes very task dependent, right?
It's not really task dependent. You can it's not task semantic dependent. It's the task structure dependent. Now we are not saying that. So you have implemented say graph coloring using and say algorithm A. Okay, of course there is an algorithm B that you can use to do that. We are not saying that you are not choosing the most efficient algorithm. That's not what we're doing. That's actually even a higher level semantic operation. What we're seeing is that in your implementation of algorithm A in the GPU, are you actually writing that software in a most efficient way, or whether it has actually functional bugs on it. It's not at the algorithm level. At the specific software that you're actually providing, that's what we are tracking.
Was the out-of-bound access detection at compilation stage?
We did it on the lens. It's currently under submission.
Okay. Any more questions? Looks like everybody is hungry. Yeah. Questions? Come on.
Hello, sir. So I was trying to understand the second part of your lecture where you were talking about over synchronization. So what are those metrics that you use to detect this kind of over synchronization in the GPU?
We don't use exact metric. What we actually do is that we analyze the program. We also know the semantics of each of the synchronization operation from, say, the CUDA specification, right? And then we find cases where you are actually doing more synchronization than needed. Okay, it's just that redundant or over synchronization that we actually look for. It's not exactly metric, right? So we are not. So and then we actually fix it, and once we actually fix it, and then based on sometimes you get like 10% performance improvement after the fixing, the over synchronization or removing the redundant synchronization, or sometimes you get 30% performance improvement. So that is not in our control. What is in our control is to see whether there is an extra synchronization work is happening or not through program analysis. And if it is, we suggest that this is, you can actually do away with less amount of synchronization, and that may or may not improve the performance.
When you say that there is a 10% improvement in the performance or 30%,
there are also cases, I didn't get your time, there are cases also 0% improvement.
Yeah, but how do you measure this performance improvement?
Okay, so these are actually one line fixes and so on. So for example, typically total number of, if I remember correctly, the number of lines that you have to change is very minimal, like 19 lines all together, all application. It is because what you do, there is a synchronization operation or say barrier operation after a fence, you just comment out that barrier operation because that's not needed. Or you have a thread fence, which were actually white thread phones, you change just the qualifier to use a block scope. Okay, that much. So there's not much performance code changes you have to do. But the way that we get it is that after our tool tells that there is over synchronization, okay, we change this 1 or 2 lines in the code and then run again to see how the performance is actually improving. And sometimes you don't get performance improvement. That can happen too.
Yeah, actually that was my question. Like when you detect over synchronization, you make some changes and again you run. So you would have measured the performance with some parameters in the first stage and after.
Yes, so that is the performance improvement in the second.
Yeah. So what are those measurements that?
This is just a runtime.
Just a runtime. Okay,
yes.
thank you.
Yeah. There's some secondary metric too, but like at a high level we are just looking for how much performance we are improving runtime. Yeah.
On that note, actually, yes. So what I understood is you basically have like a baseline code, right?
Yes.
That gets passed to your tool, and then that converts it into like finite states, and then kind of looks at where you can synchronize, or like what's the conversion?
Yeah. So what we do is that that we didn't go through. What we do is that the basic idea is this. So you actually break the program in multiple windows.
Right.
Because the windowing is in there. You need a portion of code that can run in parallel and then you need to synchronize. That's how the programs are. And then you find at each synchronization point, this delimiter is always a synchronization point, and see if this synchronization was needed for this window or not, or the strength of that synchronization is needed for this window of code or not. That's how the analysis actually happens.
Okay, so basically,
break it up.
So basically, it's like you have defined the microarchitecture and you have a filter.
I don't need to actually define the microarchitecture.
I mean, you're assuming that it's.
So we run on the thing that we have to actually do is actually run on the program level and the programming language level. So I don't care about how exactly the GPU hardware implementing something. I'm actually looking at what are the guarantees the programming language giving us, like for example CUDA. So I'm actually correct with respect to it. How exactly that particular program is implemented in a given, say, Hopper architecture versus Barker, it's not my problem. It's the NVIDIA's problem.
Okay, thank you.
Yeah. Any other question?
Any more questions?
So this can go in compiler pass, right?
Yeah, this was actually a binary tool. There are actually ones that we actually do. There are other works which actually run on the LLVM pass. So the problem with the NVIDIA is that NVIDIA's own internal compiler that is not open source, but there is an LLVM pass. LLVM also can compile CUDA, right? So we actually do it on the LLVM.
So this issue can be settled at IR stage and then.
Yes, IR state. So there are multiple levels of tool actually built. We have bunch of tools which actually run on the binary instrumentation side. That actually builds on NVIDIA researchers. There is a tool called NVBit, like a pin tool, if you know, for the CUDA programs. So the advantage of that is that it can also work on closed source program, because so the set of tools that we have for static analysis, the compiler one, their limitation is that you need to have the code for them to actually analyze. This one actually runs on the binary.
Okay, let's thanks Arka for the wonderful talk.
Thank you.
Okay, now we'll break out for lunch, but now I'm going to give you a very complex algorithm for lunch, which is much more complex than Arka's talk maybe. So you will see that in the CSA garden there are 2 lunch stations, okay? Because there are 2 parallel events going on in the department today. Actually there are 3, but don't go into that complexity. So go have a lunch where the CSML workshop poster or direction is there, okay? The lunch is at the same place, the back side of CSA garden. And to remove any like misunderstanding, you can go through the corridor. If you remember on the first day it was raining, so you went through the corridor and took the back gate in the garden. So go through the corridor and take the back gate to the garden. Any question? So this is very important. So don't grab other conferences lunch.
If I were you, this is the algorithm I would have used. I would have checked the food on both the places and picked the one that is better.
Please don't do that. Okay. Then probably I can say maybe our food is better.
Maybe his problem, not also understand which one can be your problem, which can be somebody else's problem. Maybe his problem. Who cares?
Okay. Any question? So okay, the simple solution is just go and grab lunch wherever you had lunch in the past 3 days. Okay. So thank you. We'll meet at 1:50.
Yes. So from what I understand, you work at the software level. I don't think you touch upon the micro architecture level.
I used to, but not exactly.
Oh, okay. Because today all the so when you take system to our lab and build stuff, I announce. But keep volunteers there so that they can guide you. Okay? Yeah. Because the other people don't want to get interfered. I am fine if some other people have that question, but the other workshops they don't want to. Okay? Yeah, I'll talk to you. Just be outside. Just be outside. Okay? Whatever is being told, do that.
No, this is 3 days. Okay. And on that, we have managed to put this into a VR headset and we're able to connect it to other systems in that. So we can bear it